what's it called, like an entry vector, and moving them into double antibiotic assembly vectors, and from there you can do this like pretty efficient like double antibiotic assembly that scales up fairly well. So I mean, one of the things that like Chris has been trying to do in his lab is come up with mechanisms for doing all these things that scale up well, so we could do high throughput making of parts and things like that, and because that's essentially where we would like synthetic biology to go, and where we would like our lab to go with it. And so the gateway reaction it's been a fairly clean way to get things from the entry vector into these double antibiotic assembly vectors. And then there's actually a final gateway reaction step at the end where things would be taken out of the assembly, the double antibiotic assembly vectors, and put into destination vector. Right now we're dealing with the initial gateway reaction. Yeah, I think that's pretty much it. Okay. Oh, I kind of forgot about another part. But
what's that?
Like, so another one of the things that I'm working on, because I seem to be working on a lot for some reason. So I am doing things. So I talked about gateway, and now once you do gateway, you can do assembly. So I'm also working a little bit on some of the assembly stuff. So, I mean, the basic parts that I made, the BAMH1 and Bagel2 restriction enzymes, the Cre enzyme that interacts with a LOX site and does a LOX recombination, and ligase that kind of like DNA glue and glues things together. So like I made those basic parts. Right now I'm making some composite parts with those, and we're hopefully going to be working on like doing assembly. Like our ideal situation was doing assembly in the lysate. We're still in the process of testing whether that's feasible and seeing like what sort of conditions we would need for that. And there's the other scheme, or like the other possibility of doing assembly in the cytoplasm. So, I mean, right now we're trying to focus more on gateway just because we're farther along in coming up with the schemes that we think are going to work. We've eliminated some possibilities of things that don't work or don't work so well. So we're a lot farther with that. So right now, at least for IGEM purposes in the Jamboree, we're trying to focus on getting that done. But I'm also doing some work on this assembly stuff.
Fantastic.
Yay.
So, what do you think, well, how about I ask this question first? Do you think there are any ethical problems associated with the IGEM project that you guys are doing?
With the project that we're doing, I don't think there's very many ethical issues. I mean, at most it might be like we're evading Invitrogen's monopoly on the gateway, the gateway enzymes, because they do sell they do sell a kit for gateway which has this enzyme mix, and it's pretty expensive. Yeah, so I think it's about $6 per reaction. So once you start scaling up and doing multiple reactions, it's definitely something that is pretty expensive. But besides that, I don't think there are too many ethical things ethical problems with what we're doing. Like the lysis device we're using is from a phage. Like, I guess it could potentially be reused for something, but I don't really see that very much as a problem.
What do you think synthetic biology, like the place for synthetic biology or its role in our world? What do you see that as? It's very grand.
Yeah.
Yes, so grand. I'm having a hard time explaining. I mean, you could look at it two ways. It could be, what do you think you would want to use synthetic biology to do, or what do you think could be done? I mean, how do you measure, like, the use of synthetic biology? What do you think its benefits are, or if it is really beneficial?
Yeah, okay. So I think synthetic biology has the potential to be very beneficial for society. I think there are a lot of really great, interesting projects along the lines of creating a lot of things with therapeutic applications. I mean, the tumor killing bacteria project, I talk about that one a lot because it's the one I'm the most familiar with. But just in general, kind of the idea of using something that's biologically based for therapeutics is that you have the possibility for increased specificity in targeting things. So, I mean, that's one of the big problems with cancer therapeutics right now. A lot of chemotherapy just targets everything, and then you get so many side effects. So just having that increased specificity that is kind of, it's a lot more common in biological systems than it is in chemical systems. So, like, just taking advantage of that in therapeutics, I think, is really promising and can potentially, it can totally change the field if, like, there are successful projects in that sense. There's also a lot of great projects using, like, synthetic biology for the environment, but, biofuels, bioremediation. Yeah, just basically engineering them to, like, solve, like, there's so many large-scale problems, and I think synthetic biology can be used for a lot of them. Not all of them, but definitely significant things.
Do you think so? You do think there's a limit to what can be designed, essentially?
Yeah, I mean, I think that synthetic biology has its limits in terms of what sort of problems it can target. I don't think it's necessarily, like, I don't think it would be the right solution for an approach to population control, or, like, or there are a lot of other things that, like, you're going to need biomechanics, and, like, maybe once you find the proteins that are involved in mechanical responses, you can use synthetic biology to, like, manipulate them. But, like, I mean, like, some things, like, you can't use synthetic biology for everything.
Do you think it should be coupled? So it's double helix, right? The magazine that you're...
Triple helix.
Triple helix. So can you explain to me a little your involvement with triple helix?
Okay. So the triple